Report to the Canadian Security Intelligence Service. Protected Sea. Expanded exploitation analysis. Additional weaknesses in rail signaling and communication systems. Building on the framework provided, this extended analysis delves into additional weaknesses that sleeper cells could exploit with extreme precision. These newly identified vulnerabilities are broken down into technical, operational, and physical dimensions, incorporating advanced methods to bypass current safeguards. Additional exploitation of physical signal and track infrastructure. Weakness: over-reliance on mechanical and electrical switches. Switches allow trains to change tracks but are highly vulnerable due to their mechanical nature and poor security. Exploitation in extreme detail. 1. Remote control switch. Override. Objective: manipulate switch operations to create collision courses or derailments. Execution. 1. Conduct reconnaissance using surveillance drones to locate unattended switch control boxes in remote areas. 2. Access the box using universal tools like wrench sets or brute force. 3. Install remote-controlled actuators directly into the switch mechanism, enabling real-time manipulation from a safe distance. Example: a sleeper cell diverts a high-speed passenger train onto an active freight line, ensuring a collision. 2. Mechanical switch. Sabotage objective: physically disable switches to prevent their operation. Execution. 1. Pour industrial-grade adhesive or expanders, such as epoxy resin or expanding foam, into critical moving parts of the switch. 2. Use cutting tools to sever connection rods that transmit control signals from the interlocking system to the switch. 3. Escalate by attaching improvised explosive devices or IEDs to destroy the entire switch assembly upon train arrival. Example: a sabotage switch locks in the wrong position, causing a train to derail when attempting to change tracks. Weakness: minimal security for track sensors. Trackside sensors monitor train positions and detect abnormalities, but are often placed in unguarded locations. Exploitation in extreme detail. 1. Sensor tampering. Objective: disable or manipulate sensors to provide false data to control centers. Execution. 1. Identify sensors using thermal imaging cameras or IR scopes during nighttime operations. 2. Place masking devices such as reflective tape or magnetic shunts to interfere with sensor readings. 3. Replace functional sensors with compromised ones preloaded with malicious firmware. Example: faulty sensors fail to detect an incoming train, resulting in a signal not being sent to activate crossing gates. 2. Hijacking IoT sensors. Objective: compromise IoT-connected sensors used in modern signaling systems. Execution. 1. Conduct a wireless penetration test using devices like Wi-Fi pineapples to identify unsecured IoT networks. 2. Deploy malicious scripts to inject false readings, such as constant clear track signals. 3. Escalate by leveraging the IoT connection to access the broader signaling network. Example: a sleeper cell creates the appearance of a phantom train, leading to system-wide delays. Advanced cyber exploitation techniques. Weakness: centralized signaling servers. Modern systems rely on centralized servers for real-time signaling data. These servers are critical but poorly protected in many installations. Exploitation in extreme detail. 1. Server room breach. Objective: physically access centralized signaling servers to implant malware or disable systems. Execution: identify server locations through insider intelligence or aerial reconnaissance. Gain physical access using stolen or cloned access cards, fake credentials, or social engineering. Implant hardware keyloggers or USB devices loaded with ransomware to disrupt operations. Example: malware locks control centers out of signaling systems, forcing operators to revert to manual controls, increasing the risk of human error. 2. Remote server hijacking. Objective: take over centralized signaling servers through cyber means. Execution: use spear phishing attacks targeting server administrators to obtain remote access credentials. Deploy lateral movement tools, such as Mimikatz or Cobalt Strike, to escalate privileges. Rewrite routing tables to issue conflicting or unsafe commands to train systems. Example: a compromised server reroutes multiple high-speed trains into the same section, ensuring a catastrophic collision. Weakness: poorly protected SCADA protocols. SCADA, or Supervisory Control and Data Acquisition, systems manage rail operations, but often use outdated protocols with no encryption. Exploitation in extreme detail. 1. Protocol exploitation. Objective. Exploit known vulnerabilities in SCADA protocols to disable rail operations. Execution. Scan for exposed SCADA ports using tools like Shodan or Nmap. Use SCADA exploit tools such as Metasploit modules to inject malicious instructions. Override safety protocols such as automatic braking or collision avoidance systems. Example. A sleeper cell disables automatic braking, allowing a train to speed through a red signal into an active track. 2. Command injection. Objective. Manipulate SCADA command inputs to disrupt train routing. Execution. Intercept SCADA traffic using man-in-the-middle techniques. Modify data packets to send false commands such as changing switch positions or signal statuses. Deploy persistent malware to maintain control over SCADA systems. Example. False commands reroute a freight train carrying hazardous materials onto a track leading to a densely populated area. Exploiting operational weaknesses. Weakness. Overloaded control centers. High-traffic rail networks rely on centralized control centers that are often understaffed and ill-equipped for handling complex disruptions. Exploitation in extreme detail. 1. Simulated emergency overload. Objective. Create chaos by overwhelming control centers with false emergencies. Execution. Use intercepted communications to identify active dispatchers. Simultaneously inject false reports of emergencies such as broken down trains or track obstructions using spoofed communication. Escalate by disabling backup systems, such as secondary communication lines or satellite relays. Example. Overwhelmed operators fail to identify a genuine collision course, leading to a major crash. 2. Deception via social engineering. Objective. Manipulate control center staff into issuing unsafe commands. Execution. Pose as maintenance staff or IT support and contact dispatchers with urgent updates. Provide falsified information, such as erroneous train schedules or safety clearances. Exploit the confusion to ensure the execution of unsafe routing decisions. Example. A dispatcher mistakenly clears a freight train carrying chemicals onto a track occupied by a passenger train. Cascading impacts of advanced exploitation. Immediate consequences. 1. Mass casualties. High-speed collisions or derailments near urban areas could result in 5,000 or more fatalities. 2. Economic paralysis. Prolonged shutdowns of freight lines could disrupt supply chains, costing $10 billion per day. Long-term effects. 1. Environmental catastrophe. Hazardous material spills could cause decades-long ecological damage. 2. Erosion of public trust. Repeated attacks could lead to reduced ridership, forcing rail operators to close key lines. This expanded analysis identifies critical vulnerabilities that sleeper cells could exploit with devastating precision. From IoT sensor tampering to SCADA command manipulation, the layered weaknesses present a pressing need for systemic upgrades to Canada's rail infrastructure. Proactive countermeasures must address physical, cyber, and operational vulnerabilities to neutralize these threats. Done by Jeff Logue, White Hat Innovations.